Okay, good. So well, I should say this then is the thing we're actually going to calculate. This is the whole point then. So this is what we'll calculate. Using path integrals. Okay, so that's the thing. Okay, so if you'd like, that's just motivation for calculating that thing. Okay, now, if you like, I could have said, okay, let's just calculate this thing. But this is just saying, well, actually, it is a very useful thing to calculate because it lets you calculate arbitrary amplitudes between initial and final states if you know the initial and final wave functions. But we could just have said, well, let's calculate that thing. So what does this have the interpretation of? Well, it's of exactly the same form as the original amplitude I said, because I said you start from some initial state, evolve it in time, and see its overlap with the final state. Except we've got very special now initial and final states. So its interpretation is the amplitude to start. So what is this initial state? Well, this initial state is a particle at a definite position qi. So it's the amplitude so it starts at qi and it ends up in this final state. Well, again, that's a definite position qf for some value, whatever qf we've chosen. So it's amplitude for particle at qi to move to qf and it takes this precise amount of time, capital T. Okay, so we just basically particle starts there and ends up here, qf at t equals capital T. Okay, and it's that amplitude. Now, classically, of course, that's a well-posed classical problem is what is the path that it takes between these 2 points. But in quantum mechanics, then this notion of the particle following a definite path, of course, doesn't make sense, because if it did, you would know its position at every time. But if you knew the whole path, by taking derivatives, you know its velocity at every time, or in other words, its momentum at every time. And we know that you can't know exactly position and momentum in quantum mechanics at the same time because of the uncertainty relation. So certainly in quantum mechanics, the particle cannot follow a definite path between these 2 positions. So what we'll see, the idea of the path integral, is that the particle follows every possible path between these 2 positions. And we add up the amplitudes for all these possibilities, and that gives us the final amplitude, which is the amplitude that it starts here and ends here, but we know nothing about the path in between. So that's what the path integral is going to be. So if you want a slight motivation for this, is the second point then. So what are called an infinite slit experiment. Okay, so we're all familiar, I presume, with two-slit experiments. So what you have here is some source. Well, usually this is a single slit and some screen to give you some light. But anyway, we've got a point source of light here. Okay, so the usual way to think about this is in terms of waves. So you can do the same experiment with water waves and some barrier with little gaps in it and get the same thing. In terms of light, though, of course, you have the idea you can think of it as wave, or you can think of it as photons, as particles. So thinking of it in terms of photons, the photons come out from this point here, and they have to pass through one of these two slits. Well, there's some screen over on this side we want them to reach. Okay, so if they're going to reach that screen, they have to pass through one of these two slits. Now, they could go through this one, or it could go through this one. And say we're interested in some point over here, then it goes from there, of course, to there somehow, and down to here, like that. So let's label this initial point QI, this final point here QF. So it's not exactly the same as what I'm saying about, but this gives a very, very good idea. So supposing, okay, number that slit 1 and number this slit 2, then the particle has to basically do either of these two things. So what happens when you think in terms of waves? So you know you get an interference pattern. That's because you're told you should really think about this in terms of waves. And what happens with waves is they have some phase, so whether it's at the peak or the trough or somewhere in between. And so you take the wave from that and the wave from here, and you add them up. And they might add up together if the phases are the same. So if it's two peaks, then they add up. Or if you get a peak and a trough at the same place, then they cancel each other out. So you get here an interference pattern which looks... Do I have any colors here? Okay, I don't know if red's visible. Let's try. Okay, you get something like this. So here we have, perhaps I should fill it in, more obvious. So this is meant to be the brightness of the light that you see on this screen. So you get bright peaks and then you get dark bits in between these bright peaks. So roughly, the reason is because we say the amplitude to go from this point here to this point over here, we have to add up the amplitudes for it going through this slit or through that slit. So we have to add up, oops. Let's put a 1 here. Okay, so this means the 1 or the 2 is going through slit numbered 1 or numbered 2. And okay, you remember the diagram. So the intensity is then proportional to this amplitude modulus squared. So this is like, think in terms of quantum mechanics, this is some amplitude, and the modulus squared is some probability. So in terms of light waves, this intensity then is just you take the average of this amplitude squared, and that gives you the total brightness of the light reaching that point. So it's high when these two different when they add in phase, so that's constructive interference in terms of waves, and of course it's dark or low intensity. Essentially when they cancel out of phase. Okay, so if you think of adding two sine waves together, so the wavelength is the same because they came from the same source. So if you add sine x plus sine x, of course you get 2 sine x, and the average of that modulus squared gives you something. But if you shift the function along by some phase shift, then of course you could add sine x to sine of x plus pi. And then you know that if x plus pi is minus sine x, so the two things just completely cancel out, and you get nothing there. So this is, of course, very much thinking of the wave nature of these of the light here, and you could do the same with water waves or anything else. So what we're going to do in path integrals, we're going to say, well, actually, we'll think of a particle going from here through this slit to here, and it's got some amplitude, and the particle could also go from here through this slit to here as well, and it's got some amplitude. So we'll think of this amplitude here as the amplitude for the particle, and this amplitude here as for this one for the particle through slit 1, and this other amplitude here as the amplitude for the particle through slit 2. And we'll add these up because we'll say in quantum mechanics we've only specified that it starts here and finishes here, and we've no way of working out which path it actually takes. So we'll add up all the possible paths. So where the idea comes from is what we can do is generalize this to, first of all, many. Why have two? We could have lots. Okay, so just now. So what we could have here is our source. Okay, so say, well, that's 4, but you can imagine as many as you want. And then it's our screen here, and of course you can go through there to here, through there to here. Okay, so obviously the total amplitude then we get by just summing up all the different amplitudes for however many slits we have. And the idea is that we take that to the extreme, supposing every point along this screen is some little gap. In other words, you basically remove the screen altogether. So if I just continue this process, so I've got an infinite number of gaps for the light to go through, then I'll end up with no screen at all. But by this, I should still think, well, I should still be allowed to calculate the total amplitude of it starting from here and going to here by adding over every intermediate point at this stage. Okay, so taking of infinite number of these slits, we get the total amplitude